So, today we start small world. So, tell me the definition of small world. Distance small, okay, and clustering coefficient is high. Okay. So, these are the basic 2 points which guide small world. Okay. So, it is a graph or it is a network where distance between 2 points is high, is small, low, average distance between 2 points is low, while clustering coefficient is high. Okay. Can you give me a example of small world, a graph? Okay. So, immediately what comes in your mind is click. Okay. Yeah, star is not a star has no clustering coefficient. Okay. Okay. So, click. Okay. So, but is click a small world? Actually not. Okay. Not by the strict definition. Why? That means click satisfies both of this. Then there is a third condition also. What is the third condition? No, it is not power law. It means we do not talk about the degree distribution. It can be anything. Huh? So, what is special in click? Huh. So, very good. So, tell me what is the third condition for small world? Sparse graph. So, if it is a dense graph, then most probably these things will be satisfied. Okay. Satisfying these two property is easy. Okay. But if it is a sparse graph, then it becomes a challenge. So what can we think? Can we now think or more abstractly define the graph structure of a small world? Yeah, very good, very good. So, I take your word what you have said, multiple community. I will not use the term community because it has other implications. I would rephrase it and think it in this way, that it is locally dense, globally sparse. I think global will have 2L, huh? Double L. Okay. So, is this concept clear? Okay. So, it will have somehow, means I am not telling any scientific term, but I am just thinking aloud that it will be somewhat locally sparse, locally dense and globally sparse. Okay. Okay, very good. Now, what is the first graph we have learned? Is the random graph. Okay. So, random graph satisfies this property. Okay. distance small. But what is the clustering coefficient of a random graph? So, what is the construction of a random graph? Can we again say? So, each connect with probability p. Okay. Each connect with probability p. So, what will be the clustering coefficient? So, very simply we can think that triangle by triplet, it will be some order of triangles by triplets, whatever definition you go. That was, so formation of triangle is p cube, while formation of p square. So, C C will be of order p, and when limit n tends to infinity, p tends to 0. So, C C of a random graph is 0 or it tends to 0. Pratik, bolo. Where is L? Its limit n tends to 0. So, I think I am clear. So, what happens immediately? Random graphs, or means, so this can be suitably extended to any random graph. Okay. It is not only ER, once this is a ER graph which we showed, but this is the same explanation can be extended to any random graph. Okay.
How can you say that it has small distance?
Random graph we have seen, no, it is Z2 by Z1, if you remember. One is equal to diameter, if you something like this we studied. So, n is, it was log, the diameter is log n. I am sorry, this is d, this is n. So, diameter is of log n, that was we studied. Okay. So, most of the random graphs, all random graphs will have diameter log n. So, if it scales to log n, we say that it is small, okay, while the clustering coefficient is low. So, last class when we were talking of power law construction, we talked about that there are two algorithms. One was which we really studied was bipartite clique, introducing bipartite clique. The other which we did not study was somehow to increase clustering coefficient, that we mentioned, but we did not study. So, any random graph unless forcefully done will have low clustering coefficient. Okay. So, now let us think again with this principle, okay, locally dense globally sparse. Okay. So, locally dense means local cliques existing. Okay. So, I just try to okay. So, a local clique. Okay. Okay. Now, what we do? We remove this. put it here, and then again we have, I am bad at drawing. Okay, remove this again. Okay, so this goes on. Remove this. Okay. So, this is clear. This may be a better drawing. Okay. So, basically you see there is local denseness, while in the global perspective everybody has connectivity or how much? Yeah, everybody has connectivity, average connectivity is 4, and number of nodes here are 1, 2, 3, 4, 5, 6, 24. 30 nodes each has connectivity 4, and this can be suitably extended to 300 nodes each has connectivity 4. But the local locally each locality is dense. Okay. So, this is the first model which we can conceive. Now, we have to see what is the clustering coefficient of this model and what is the diameter of this model. Okay, agreed? Okay. So, I just try to write that I want to find the clustering coefficient, I want to find the diameter, and this model is basically called a connected Kaufman model. It is basically called a connected Kaufman model. So, if you think of ad hoc networks or if you think of mobile phone networks, okay, you will see this connected Kaufman model applies, because all of if I think it does not apply really just now, but if we think concentration of mobile phones and if you think that these mobile phones can interact with each other, then you will see in this class you have huge concentration of mobile phones. Okay. Then in that lab, the assumption is the mobile phone can only interact at short range. Okay. If I think that I want a Bluetooth connection, then it is a short range connection. Okay. So, that way this connected Kaufman model is a very realistic model. Okay. So, what we want to see? We want to see whether this connected Kaufman model is a small world or not. Okay, agreed. So, we are not interested in betweenness, we are interested in clustering coefficient. Okay. So, we want to find two things: clustering coefficient, second is diameter. Okay. So, let us see again. If I put this thing in perspective, then I will draw. You have 1, see there are 4 types of node. Okay. There are 4 types of node. So, class you can, and this is similar in every cases. So, if we can find the clustering for coefficient of each type and sum it over suitably weighted sum, then we get the clustering coefficient of the entire network. Okay. Okay. So, now let us see the clustering coefficient of B first. Okay. I will try to find CCB, CCA, CCC and CCD. Okay. Tell me the clustering coefficient of B. So, let us see B. So, B has how many triplets? See, 1, 2 and any further? Yeah, this one and this one. Okay. And all these triplets are ultimately converted into triangle. So, CCB is 1 straight. Okay. CC, so let me think aloud. So, if I think that number of nodes are k plus 1, this is 5 I have drawn, but I could have drawn it anything, okay, 10, 15. So, then how many connectivity it has? K minus 2, because one connection it does not have, this connection it does not have. Okay, so how? Huh? So, it is k minus 1. K plus 1 nodes are there, and you can have, each can have at most k connection, but this does not have one connection. So, it is k minus 1. So, how many pairs are there? K minus 1 C2 pairs. Number of triplets are k minus 1 C2 and number of triangles are also k minus 1 C2. I just wanted to show because it will be important for the second one. Okay. So, okay. So, for the second case what happens? How many connections? Okay, I take A. Okay, I take CC A. Okay. How many connections are there? KC2, okay, because it has K connectivity and KC2. And how many triangles will be formed? KC2 minus 1. Okay. Okay. No problem. So, that is okay. So, that will actually become 1 minus 2 k minus 1. Okay, just one connection is not there. Okay. Okay, CC C. No, C has this connectivity, huh? So, how many connectivity it has? So, k plus 1 C2. Now, how many triangles? See, this does not form triangle with any. So, all this k plus 1 triangles has to be eliminated. See, this does not form triangle with any. Okay. So this can form how many triangles? K. See, first of all, total number of triangles is k plus 1 C2. Now, this pairs with how many? K, and that none of them form triangles. So, that minus k, and see here their triangle is not formed in this case. So, another. Yeah, you are correct. It's k serum is 2 minus 1. Okay. So, this is 1 by k plus 1 C2 k plus 1 Okay. So, this we after some simplification it comes as 1 by minus 2 pi. Okay. CCD is what? So, CCD also, so okay. So, I just draw this again. Okay. So, C A B D. So, we can see that again CCD will give this is easy, I am not doing it. Okay. 1 minus 2k. Okay. So, when we do CC for all, it will be how many A types of node will you get? Okay. 1 by k plus 1 I write, because these are the types of node. How many A types of node you get? K minus 2. Okay. K plus 1 minus 3. Only these 3 are special, everything is A. Okay. And that is how much? We wrote it is 1 minus 2 k minus 1 plus 1 plus 2 into both CCD and CCC has 1 minus 2 by k. This is CCD plus CCC. Okay. Is it okay? So, this is CCA, CCB, CCD. C and D both together, that is why I wrote 2. And this with some calculation you can see it comes as okay. Okay. So, as n tends to infinity, as n tends to, what are the conditions? Distance small, CC high and sparse, 3 conditions. So, if n tends to infinity, in order to have sparseness condition, what can k be? No, k can also tend to infinity. As n tends to infinity, k can also tends to infinity, even then we will have sparseness. Yeah, k by n should be small, or k by n should be large, n by k should be large. No, k plus n, 1 is just a part. No. So, what we told that this is 5, this is 5, while the entire thing is 30. So, this is n and this is k plus 1. So, the point is n can tends to infinity, at that point k also can tend to infinity, only concern is should be reasonably high. Am I right with the spelling? Okay. High, forget reasonably. Okay. Okay. It should be high. That is the only constraint for sparseness. So, if k tends to infinity, then C c when n tends to infinity and k tends to infinity, what will be the C c? 1. So, the first condition is satisfied, that a connected Kaufman with our first intuition that locally dense, globally sparse, this is holding, and immediately we see that we can have a network with high clustering coefficient.
Why this graph is called a Kaufman graph?
Yeah, because it is simple that there are caves and which are connected by some tunnels. So, that is the original. Yeah, in social networks people model caves like that. That is the first concept. So, the name cave. Okay. Okay. Hmm? No, it is not necessary, but I am telling that you can model the Kaufman with suitable parameters and bring C c to 1. Okay. So, but what is the diameter? Tell me the diameter. Okay. This again C Kaufman. Tell me the diameter of it. So, if we think these are points, okay, if these are points, so basically diameter will be n by, so each has k plus 1 elements, 1, 2. Okay. And what is our assumption? See, immediately see this assumption. Our assumption is n by k should be high. Okay. So, then what we can say, diameter, if n by k is high, dia will not scale, dia will is a polynomial function of n, or it is just a proportion of n. Okay. But dia will not scale to log n. Okay. So, dia will not scale to log n. It is the diameter, because you see, you think that number of elements here is very small. So, the probability that 2 elements will be inside a cave is very small compared to the probability that 2 elements will be in 2 caves. If I think, okay, so if I think very minutely, then what should be its probability that a pair in a cave into diameter local plus probability pair in 2 caves into diameter global. And then what we thought, that since k is small and n is large, this will tends to 0. So, this we can ignore and we can say that it is D is equal to actually, so this tends to 1 and this tends to 0. So, D is actually D global, and D global is we see 2 k plus 1.
It is only possible in ring network, but if these small entities are connected with any node or 2
Yeah.
or 3, then it will be logarithmic of n by k.
Yeah, so very good. So, we will see that how this is the basic model. The one thing we wanted to drive home is that, see, first of all, what I have told you, this connected Kaufman has many real life application, like in ad hoc networks. Means in networks there are really applications of connected Kaufman. Like if you work on delay tolerant networks, you will immediately see that there are connected Kaufman problems coming on, because you have local connectivity, but global connectivity is not there. So, you can use this to analyze delay tolerant networks like. Okay. So, this is clear. So, that is why, since this has a real life application, I am first concentrating on understanding those real life applications. Second, what you are suggesting, that can we modify this simple model to make it really power law and make it really small world. Okay. Clear? Okay. So, now I come to the real small world, okay, which was first suggested by Watson-Stokes.
In the previous diameter,
Huh.
n by 2 into k plus 1 is the maximum distance between 2 points. But when you wrote probability that two nodes lie in different clusters, and then you wrote diameter global, but they might lie in 2 clusters which are adjacent or separated by only.
But average, you take the average. On the average, it will be d by 4.
Diameter is anyways maximum. We do not need to consider any average.
No, I have misnamed it. I think distance average. If I shouldn't tell it diameter, I am just thinking distance average. So, d global means it can be adjacent, it can be far, but what is the maximum taken is d by 2. This is the maximum taken. So, average will be actually d by 4. So, it can be adjacent, but it can be at most by 2. So, it will be 4. No, this is not a small world, because n by k is large. So, n by 4 k is always large. Okay, this is not a small world. We have to somehow modify it or make it small world. And what Afaq, what Afaq was suggesting is that we can randomly connect it and somehow make it small world. Okay. So, we come to that. So, that is why we are coming to the real small world problem of which was suggested by Watson-Stokes. So, Watson-Stokes took a simple grid. Okay. Simple grid with k connectivity. So, I write, let us see, k is equal to 4. Okay. So, everybody has this k connectivity. Okay. It's a cellular automata type of thing, that where everybody has k connectivity. Okay. Means 2k connectivity, k is the neighborhood, is the radius of each cell. Okay. K is the radius of each cell. Okay. So, now can you find the clustering coefficient of this grid? Yeah, it becomes circle. It is a periodic boundary, we always. So, let us try to calculate the clustering coefficient of this Okay. So, first of all, say number of triplets formed. It has 2k. So, 2k C2, that is so 2 into 2k into 2k plus 1, minus 1, oh sorry, by 2. Okay, am I with you? Okay, very good. Now, how many of these triplets have formed triangles? That is what we have to find. How many of these triplets have formed triangles? Okay. So, let us see. Okay, I write A, B, C, D, E, F, G, H. Okay. So, let us consider A. Okay. A will form how many triangles? A will form triangles with this, because there is a connection from here to here. So, it will form triangles up till here, beyond, because it also has k connectivity. It also has A also has k connectivity. So, A has connectivity here, connectivity here, connectivity here, and this connection. Okay. So, how many triangles because of A are you getting? Okay. Triangles because of A is k minus 1. Okay. Triangles because of B. So, this I don't see the right side. Right side is has already been taken care by A. So, it here, this is already there, and then here, because it has k connections 1, 2, 3, 4. Okay. Are you convinced that it is also k minus 1? Okay. Okay, very good. So, now triangle C is also k minus 1. This, so now come to E. I hope triangle up till D is okay. E 1, 2. So, E also has k minus 1, no problem. Okay, very good. So, now F can have only k minus 2. F cannot have k minus 1, because there are no k minus 1 cells left, it is k minus 2. Okay, I just write it like this. Then G okay. Yeah, it will go on. So, k minus 2, because you see here there are no k, how many spaces are left here? Just k minus 2. Means you have to have a connection from because what are you trying to find? Clustering coefficient of x, and x has connection till h. Beyond that, x does not have connection. Because I am going this way. Yeah, because when I have seen the number of triangles formed by A, already I have seen some triangles formed by B. that is why I am just going this direction, because B is also connecting here, that is not taken care. I do not want to duplicate, I just go from one direction. Not clear? Okay. So, we do it once more. Can you tell me, are you agreeing that delta A is k minus 1, triangles formed by A is k minus 1, because it is, what is triangle? That X, A and B, X, A and C, X, A and D, these are the triangles formed. These are the triangles formed. So, if I come here, it does not have so many triangles to form, it can only form k minus 2, here you have only k minus 1. ठीक है? Okay, very good. So, then now let us see number of triangles formed. So, how much is this? 1, 2, 3, 4, 5, 6, 7. So, that is,
You would actually have to generalize it for k. This is for 4.
no, it's I have written in k terms.
Yeah, you have written in terms of k, but if the actual number of connections on one side is
Yeah.
then k minus 1 will repeat for k minus 1 k times.
No, how many times? You see 1, 2, 3, 4, 5, 6, 7.
Because k is 4 here.
So, then what? Generalize it for k.
So if it is k, then it will be k into k minus 1.
No, see from here to here it is going, just the last one is not there. So, that is 2k minus 1. So, it is going for 2k minus 1, k minus 1, because this is applicable for here this, only H it is not applicable. So, only the last one it is not applicable. No, I am considering this separately. So, I am considering this separately minus. I am considering the minus, and this minus will go up till how much? 1 to k minus 2, k minus 2. Okay. This has to go, this will go up till k minus 2. So, this is basically 1 plus 2 plus up till k minus 2. Okay. I can go this direction. No? Yeah, we can write it in many ways. Just this is one way of writing. All writing or all analysis will actually lead to the same result. I think so this is 2k minus 1, k minus 1, and this summation is k minus 1 to k minus 2, that is k minus k minus 2 into k minus 1 by 2. Okay. So, then I take k minus 1 common. So, this comes 2k minus 1 minus k minus 2 by 2. And this gives us 3k . So, this is one result, triangles, and this is one result, triplets. Okay. Okay, very good. So, then what is CCX is 3 k by 2 k minus 1 divided by 2 k minus 1 by 2. Okay. This k goes, this 2 goes. So, it is 3 by 3 k minus 1 . No, this 2 is not. Okay. Two k minus 1. Okay. So, if k is, so if n tends to infinity, k can be suitably greater than 1. Okay. Then the sparseness condition will not be will not be violated. Okay. It can be suitably. So, then what will happen? 2 k by 3 k by 4 k, which is equal to 3 by 4. If k greater than 1, I can write k minus 1 and 2 k minus 1 as 2 k. It is 3 by 2 k minus 1, k minus 1, and if k is suitably greater than 1, then you have k minus 1 is proportional. Agreed? Okay. So, now what we see, then what is the what is the clustering coefficient of a grid? It is high. Clustering coefficient of a grid is high. This is clear. Okay, agreed? And now, but what is the diameter of a grid, or what is the average distance, whatever you want to say, is L by 4 k. L or n by 4 k, whatever, we are using n. N is the number of nodes by 4 k, because again we said that 2 k, it's a periodic boundary. So, you need n by 2 k to reach, and average will be n by 4 k. Maximum is n by 2 k to k, because you can go by k hops, that you you can go there, then there, then there. Okay. So, it is n by 4 k. So, what we see, even then a grid is not a small world. Okay. Very good. So, now the real experiment comes. So, in this experiment, what Watson and Stokers do, that take the grid, and reward the edges. Take the grid and reward the edges. So, for each edge, pluck the head or the tail, or because this is undirected, there is no head or tail. Let us tell, pluck the head and put it in a random node. For each edge, pluck the head and put it in random node. Okay. So, for each edge, what you do, pluck the head and put it in random node. For each edge, pluck the head and put it in a random node. Okay, done. So, now let us see, first of all, what this will actually have an impact of, that the clustering coefficient, that the diameter will begin to decrease. Okay. So, this will basically make a, we will do the analysis, but this will basically make a random network, a small random network above the grid. But let us see what will be the clustering coefficient. Okay. So, what will be the clustering coefficient? The clustering coefficient written here is, how much did we write? 3 k minus 1 2. So, this is based upon all these calculations, okay, that this 3 exist, this exists, this exists and this exists. Okay. All these 3 have to exist to have this clustering coefficient. Agreed? So, now each of them may have been removed with a probability p. So, what will be the clustering coefficient now? So, how many triangles you will have now? No, you are almost right, not p cube. How, what is the probability that they will exist? 1 minus p. So, it is just 1 minus p cube, because those triangles have to exist, means all these 3 edges of the triangle have to exist, and they will exist with each edge will exist with a probability 1 minus p. So, 1 minus p cube. So, you see what happens if p is tending to 0. So, limit p tending to 0 means p is very small. I just remove 1 or 2 edges or 1 or 2 here and there I have done. Then C c still is high. But what we see, we will do the calculation in the next class, but if p is even p tends to 0, diameter collapses. So, this is how things begin to behave. You see the rewiring probability, it is, see, it is very small, 0.0001. This is the diameter, this is the clustering coefficient. Okay. See, at very small, the diameter immediately begins to collapse, but the clustering coefficient stays as it is for a long time. So, this is the region where you basically have a small world. Okay. So, just to end, I will give the analogy of any real world network. In real world network, what happens? You have your community, and then some of you join IIT or some of you go to USA. So, then you are basically removing one of your head and putting it in some other place, and it is very realistic, that it is really modeling a real world phenomena, and that is why in this world we see small world. Okay. So, in the next class we will do the detailed calculations.